Imagine. Imagine coming up out of a subway stop or stepping off of a light rail or a max line. Imagine stepping down from the bus into the center of a large city. And now, look up. I bet what you see, and you're surrounded with both steel and masonry buildings all around you, some of which were shrouded in glass. Well, I'm here to say that that is all about to change. And that change is going to be very significant and fantastic news for the city of Portland, for the state of Oregon, but really the best news, the most impressive news is going to be for the environment. And that's, I think, why I'm standing here today speaking with you guys. The best news is for the environment. Cities across the country used to be built with wood. Schools, libraries, state houses, Capitol buildings, hospitals, apartment buildings, places of work and worship. And for some reason, we've stopped. Have you ever wondered why we stopped building with wood? Timber is our country's greatest natural and renewable resource. And yet we've turned our back on it for over 100 years. And I believe that's due to two significant events in our history. And I'll tell you about those now. The first, almost 111 years ago to this day, actually, there was a major earthquake in San Francisco. The earthquake, unfortunately, ruptured both gas and water lines throughout the whole city. And the result was absolutely devastating fires. What's interesting about that is the fact that at the time, the city of San Francisco did not want to be known as a seismic region, so pretty successfully rebranded that event to become the San Francisco Fires. And I'd say that's a pretty good PR campaign on that event. But as a result of that, across the entire country, there's a psychological backlash, and we stopped using wood in our city centers. In fact, the entire country started building with masonry ever since, and those are all the schools we went to and the hospitals that are now built around the country. A bit of irony there now, as you are all well aware since that New Yorker article, a bit of irony there is now along the whole West Coast in a very, very high seismic region, we're stuck with all these old masonry buildings, which is kind of incredible. But I think we've now figured it out. The second event dramatically affecting our use of timber in this country was back in 1994. The Clinton administration passed what was known as the Northwest Forest Plan. The Northwest Forest Plan included as one of its main tenets to never forget the human and socioeconomic impacts of this plan, but nevertheless, and it was well intended, but nevertheless, it was the most devastating reduction of both public and private forests that our country have ever seen that are available for harvest. And the result of that, and again, unintended, was a complete evisceration of the timber industry throughout the entire country. And it hit particularly hard here in the Northwest. Hundreds of thousands of jobs were lost. Thousands of mills were closed across the entire country. And it's been hard recovering ever since. And what's interesting about this is that regardless of that event here, those two events here in the United States, the materials, the use of wood have been progressing, as David mentioned, around the rest of the world, and they've been working on engineering advancements for years now, while we turned our back on our most precious and natural resource. Other countries have been advancing these materials. So what's very interesting to me is that now the impediment is no longer the material or the safety or the engineering. The impediment is actually the law. Well, we're making some great strides forward on changing that. Directly across the river from here is now the tallest CLT timber building in the United States that we're wrapping up right now. We're going to be done in about August. And this building uses timber framing up to 95 feet. And why that's extremely relevant to this discussion is that up until this building was permitted, that core, the structural system in there, would have had to have been post-tension concrete. That was the only allowable material by code. regardless of the fact, as I mentioned, there's been a lot of advancements around the engineering. But that was the only allowable material by code until this building came along. And what's really cool about this is that this frame, the structural frame, is actually a renewable resource now. And that's really the important part of this. The frame, the structural frame of a building 95 feet into the air, is a renewable resource. The inspiration for carbon-12 was a nurse log. Nurse logs, as many of you probably know, are trees. When they fall in the forest, some people believe they've only lived about half their life. Kind of interesting to think about. The second half being dedicated to offering nutrients to the next generation of life. These are fascinating features in a forest, and you can see both new saplings and great big trees burrowing their roots deep into the cores of these fallen trees and pulling what I like to think is not only sustenance, but actually knowledge as well. And so that was the inspiration for carbon-12. Let's take a minute and talk about, as David mentioned, what CLT and cross-laminated timber is and what engineered timber means. But first, let me take 1 second and talk about, as an architect, what's really exciting about this point in time for us is that our 3D modeling programs that we use in architecture are now communicating almost directly with CNC machines on the factory floor. CNC meaning computer-generated cutting machines. So we're almost at a point where you can click a button and order a building manufactured at a plant. And you can, another way to think about that is these are almost 3D printed buildings now. But instead of plastics or metal, these are made out of wood fiber, out of a renewable resource. So how did this engineering that I mentioned, how did these advancements occur? Well, it's interesting. So I'll talk about this next slide talks about post-tension concrete, which when you came off the bus, the majority of buildings are built with. Post-tension concrete means two opposing layers of steel tendons, and then encased in concrete and within formwork, and then you repeat that for the columns, and then you go all the way up a building's structure. And those are the majority of the buildings we've all seen built here in Portland and Seattle this last 30 to 40 years. This technology has been used. What's super exciting is that CLT, cross-laminated timber, is very, very similar, but using, as I say, a renewable resource. Cross-laminated timber does the same thing. Cross-laminated under high pressure, glued together, 2x6 or 2x8 material, cut precisely to fit within a 1/16 of an inch, lowered into the building, panel by panel. That panel there was about 32 feet long, 10 feet wide. The columns are done exactly the same. Piece after piece of 2x material, glued together, high pressure, cut to fit, lowered into the building, and then repeated all the way up. And so what was fun for me as an architect and for our construction firm is to be involved in that for the first time here. These panels are coming in right off the truck. 12 trucks came and delivered this entire 95-foot tall building. Panel after panel lift right off to the truck. And again, as I mentioned, within a 1/16 inch of tolerance. What's super cool is that we had, for the first time, I believe, ever in the world, we had the factory pre-finish these panels. So imagine that. So that when that panel drops into place, it's not only a renewable structural form, it was also, the underside was also a finished ceiling of the units below. And that's a huge difference. But what's curious is up to 14 inches thick, that CLT panel has the exact same performance characteristics as post-tension concrete. But one's renewable, and one's a carbon sink, and one generates carbon. So colleagues of mine up in Canada, Andrew Waugh in UK, and Michael Green in Canada, have been doing terrific work for about 10 years. And they've been doing that work for a few reasons, and they're a bit ahead of us, but we're catching up. They're doing that because these products sequester carbon. So in photosynthesis, just the act of photosynthesis, carbon goes into the tree as it's growing. Young trees actually consume more carbon than older trees, which is pretty interesting, kind of like teenagers. And the carbon goes into those trees and is captured there. So when we use those products, in buildings such as these. The carbon sits in the building. Second, very important here in the Northwest, especially based on that Northwest Forest Plan history, these products use trees usually 10 inches in diameter and less. This means that old growth forests are completely off limits for these products. The machinery can't even handle very large diameter trees as they once did, as we're moving into, so these trees are usually third, fourth, and fifth generation sustainably harvested forests, which is pretty exciting. Fire performance. Fire performance is around the world testing has proven this time and time again. Trees and these products act similarly in the fact that they char in a forest fire. You've probably all heard about this. Trees char and then protect their core. Some trees don't even drop their seeds until a fire occurs. Similar to these, we design and engineer these products so that after whatever amount of fire that building is rated for, we still have the structural integrity left because the charring layer has protected itself. And this sometimes is up to 4 hours of fire. The next one, weight, extremely impressive to me, and this has ramifications across the entire field of construction and architecture. These products, as I said, performance characteristics about the same, but wood, CLT panel, is 80% less weight. And just think about that. So a cubic pound of wood is about a cubic foot of wood is about 28 pounds. A cubic foot of concrete is about 150. And that impacts everything in construction. That impacts fuel and shipping and trucking and erection times and safety. And the most important part of that, especially in our region, that impacts seismic safety. Think of this. In 95 feet tall in the air, we're dealing with 80% less weight. 95 feet in the air. Had that been a concrete building, 95 feet in the air, we would have been dealing with 80% more weight in an earthquake. So that's amazing to me. Thermal performance, energy efficiency. The wood doesn't transmit heat or cold anywhere near as quickly as steel and concrete do. So the slabs of these buildings do not transmit heat and cool throughout their structure. And then LEED. Some of you may be familiar with LEED. LEED's been a fantastic program for the last 25 years or so, and it's taught all of us architects how to apply energy-saving attributes to the outside of a core after you've built the core. What's particularly interesting about this, and I think LEED is gonna have to catch up here, is they forgot about the core itself. So we did a quick analysis of carbon-12 and realized that our core has put us ahead 20 years on energy savings because of the carbon sequestration and another number of other measures. 20 years ahead, had we used a concrete core and applied LEED saving techniques to the outside, good windows, good insulation, great solar panels, just by the core, if we start there, you're 20 years ahead on energy savings. And let's get, and finally, and very important to all of us, the beauty of wood. So the interior of carbon-12 will all be exposed Doug fir, which is from the Cascadian Range, which is beautiful, and so we're pretty excited about that. Now, putting all those stories together, all those attributes together, let's look around the world for a second. This building, this temple outside of Tokyo, that back structure is about 122 feet tall, built all out of wood, and it was built in 670 AD. 670. So for 1,400 years, that's been standing there, and I'm sure there's been a few fires along the 1,400 years, and also there's been 46 earthquakes in excess of 7.0 on the Richter scale since that building was built. And I think that's due to three major reasons. The charring of these large timber pieces have protected it for that long. I think the second reason is about the weight. Think of that again, 80% less weight, 122 feet in the air for 1,400 years. And then the final feature that's pretty important, and it's applicable to our buildings as well, is the ductility of the joints. So ductility just goes to mean that in between each joint, beam to column, column to panel, there's a little bit of ductility, and these buildings are able to rack and dissipate that energy prior to collapse. So they dissipate the energy, and rather than building up in a critical joint, then the building collapses. So again, another great attribute. So while the USA may be slightly behind, as David mentioned, what's interesting is we're very well positioned right here. The UK and Canada have a bit of a jump on us, but right now Portland and Oregon, we are so well situated to lead on this topic. And there's a number of reasons why. One, here in Portland, pretty exciting, we have the largest concentration of CLT timber buildings in the country. We have the tallest CLT building in the country. We also have 2 world-class universities, U of O and OSU, with dedicated research teams and departments for the research of these joints and engineering. We have the fantastic forest, Doug fir, best in the world. It's really understood. It's the best Doug fir in the world, best tree, best fiber, and best beauty. Something interesting you may not know, I didn't know it, that if you cut down a tree during a full moon, it's something like 20% stronger. Something to think about there. We have the first CLT manufacturing plant here in Oregon, down in Riddle, pretty exciting. And we're also the most experienced labor force really in the world around timber that was put out of work that many years ago. And they're anxious to get back to work. They're anxious to bring their skilled labor back to these new products, and they're doing it. It's happening pretty quickly. And again, Portland and Oregon are very well situated for that. And I'd like to talk to you. This is the first time anybody has seen this building. We've got this proposed for the city of Portland. They don't know about it yet, but it's 250 feet tall. It'll be the tallest in the world. Engineered timber. We've situated it down by the post office again. No one at the city of Portland knows about it, but maybe we can pull it off. And what's interesting about this, what I'll pledge, much similar to the way the forest industry has been doing their work for the last 40 years, is the forest industry, as you probably all know, plants 2 to 3 trees for every tree they cut down, and they've been doing that for a long time. They haven't told their story very well this last 20 years, but they've been doing very good, sustainable work. I'll make the same pledge with Carbon-12. I'll pledge to plant the trees equal to those necessary to build this building prior to breaking ground. And in this way, what would be pretty exciting is this building would again be the nurse log for this next generation of seedlings. So where does that leave us? We are in a position now to, as our cities densify, people are moving into urban centers around the world, and we have people are pouring into Portland, and there's a lot of choices of how to build. And I think we've recently learned that regarding climate change, the federal government has kind of left us on our own now, which is unfortunate. So we all have to be making decisions. So as these people pour into Portland, what are we going to choose to build with? What are we going to choose to build those schools and libraries and state houses and capitol buildings? We could choose steel and concrete, absolutely. But we could choose something that's renewable, beautiful, seismically superior, insulative, sequesters carbon. Think of it. There's so many benefits to building with wood at these taller heights. Safety, everything's proven. And so now, if you just take a minute and step back off that bus, come back up out of that subway, and now what do you see? Thank you. Thank you very much.